All right, for today we are continuing our work with derivatives of tangent functions. Just yesterday it was very simple, find the derivative stuff. Now we're going to be doing a little bit more work with those derivatives. This is the first problem. Please write down this entire first problem because there are some important details in here that I want you to have on your paper. All right, so in this problem, there's really three critical pieces of information that are conveyed in this sentence. The first is what we're trying to find. We're trying to find the equation of the tangent line. So tangent line already, that's going to be pointing me in a particular direction. But of course, I need to know what to do some of that stuff too. I have an equation here. Y equals 3x plus 6 cosine of x. And I have a very particular point. Pi over 3 comma pi plus 3. Now, I need to find the equation of the tangent line. What does that mean I need to do? Derivative, yep. That should be an instant association for you. If it's not, make it one. Whenever I see tangent, I'm thinking derivative. All right, so let's start by practicing that work from yesterday. Please just find the derivative of y. All right, now as you go to find that derivative, the first question I want to ask is, do we need to use product rule for this? No, we do not use product rule. Now the reason why I ask that is because this equation that we have here, it actually kind of looks like the result of product rule, so it gets some people's minds working in the direction of product rule because of that plus in the middle. But again, I'm only going to need to use product rule if I have a function times a function. And in both of these cases, I have a constant times a function and a constant times a function. The constant can just stay there and hang out as we go through. All right, so let's find y prime. Y prime is going to equal the derivative of 3x, which is 3, and the derivative of 6 cosine of x, which is going to be 6 times the derivative of cosine, which is negative sine of x. Now, I'm going to be having to work with this going forward, so I definitely want to clean it up just a tiny bit to make it more comfortable. So I'm going to rewrite this now as 3 minus 6 times sine of x. All right, now remember we did that because we're trying to find the equation of the tangent line. What do I do with it now in order for it to give me something useful? Yeah, the next thing we do now is we're going to take our point and we're going to plug it in. And specifically, yes, just the x into the x. So I'm going to take my pi over 3 and I'm going to plug it into that x value in order to be able to move forward. Now when I do that, that is going to give me the slope of my tangent line. So I'm going to change the name from y prime to m, just so I can keep track of the fact that I just made that change. So it's going to be 3 minus 6 times sine of pi over 3. And suddenly we find ourselves having to remember our unit circle. The interesting thing about this problem is not just the practicing, seeing how we can work with the trigonometric derivatives, but the fact that this problem all of a sudden is going to start mixing some things that maybe you didn't have to mix before. And maybe bring some things back to remember that maybe you've forgotten over the years.
It's there, but it's not there.
All right, so m equals 3 minus 6 times, now sine of pi over 3. Now if I'm trying to visualize where pi over 3 is, of course, I start by picturing my unit circle. And I think about, okay, now pi over 3, that's the one that is here. So now that pi over 3, that's basically the equivalent of 60 degrees. If you're still like converting mentally in 2 degrees, that's about where 60 degrees was. Now I'm looking for sine. Remember, sine is how far up and down we're going. So I'm interested in that height right there. So in this case, I'm going up more than I'm going over, which means that that must be root 3 over 2. All right, now that we figured out what the sine of pi over 3 was, now we need to simplify this thing. So m equals 3 minus, okay, 6 times root 3 over 2. That's like the 6 divided by 2 there, so that's 3. So it's going to be 3 root 3. All right, so having gone that far, I now know what my slope is. I know what m is. And m is so important because, of course, I'm going to be writing an equation of y equals mx plus b. And so I now know what m is. But I got to figure out what b is. And so that means that I'm going to take my y value for my point. So that's the pi plus 3. And I plug that in for y. Equals my slope. And my slope, remember, is what I just found. So that's 3 minus 3 root 3. Then that's going to be times x. And x, remember, is again a coordinate that we were given. So that's pi over 3. And then that's plus b. Yes, that is our equation. Again, remember, one of the things that this problem does for us is this all of a sudden starts mixing things that we haven't had to mix before in all likelihood. But one of the things that happens in calculus is now you are really drawing on a wider basis of knowledge. You're now bringing in your algebra skills with your trigonometry skills and not just treating them as separate little units. Okay, so we now need to solve this for b. All right, let's solve this out. On the left side, that pi plus 3 is just going to stay at pi plus 3 for the moment. On the right side, I want to distribute in this pi over 3 to both of those terms. I want to multiply that out, because otherwise there's no way I'm going to be able to actually put anything together here. So, whoop, where'd it go? There it goes. All right, so now I'm going to do 3 times pi over 3. Now what is 3 times pi over 3? Pi. Because the 3 divided by 3 part goes away, and we're just left with the pi that was on the top. Now minus. Now for this one, we have to do 3 root 3 times pi over 3. Well, okay, let me just show an extra little step here. So that's going to be 3 root 3 times pi all over 3. And those 3's cancel out. So notice what we're actually left with. We're left with a root 3 and we're left with a pi. The fact that we have a root 3 and a pi next to each other, living in the same space, actually trying to relate to each other in some way, makes some people upset at math. But we deal with what we got to get. So I got pi root 3 here. And then that's still just plus b there. Don't be upset at math. You'll be there to where that seems natural and comfortable before very long as you trust what you already know. Because notice I haven't actually used any skills that I didn't have before. It's just using them in a weirder combination than I've had to use before. All right, now I'm still trying to solve this thing for b, which means now I want to move all of this extra junk here from the right side over to the left side. So that means I'm going to subtract the pi from both sides. Well, that means that those two pi's are going to cancel each other out because pi minus pi is going to give me 0 there. And then I'm going to have to add that pi root 3 to both sides. So I end up with 3 plus pi root 3 on the left side of my equation. On the right side, though, all I have left is b. So that's good. That's where I wanted b. Having done that, we now have enough to write our equation. So let's go ahead and get our equation in there. Final answer, y equals m. Remember, we know the m from back here, so I'm just plugging that in. So it's going to be 3 minus 3 root 3, that's my m value, times x, plus b. So now I just take that b that I just found and I plug it in. So that's going to be 3 plus pi root 3, squeezing it in at the edge there. Now does this look like the normal equation of a line that you've dealt with in the past? No. Is it still workable? Yes. It still gives us numbers. I mean, if this felt really uncomfortable, you could go ahead and now translate this into something that looked a little bit more typical. You could actually just calculate this as a decimal, and you can figure out what that equaled. And you can calculate this as a decimal and figure out what that equaled. And you just have some decimal x plus a decimal. That's fine. But I want you comfortable working with these radicals, even mixed with pi and everything else that comes along the way. But remember, it's the same thing as when we have the decimals in there. We're just giving the exact form. All right, now as you are finding f prime of x on this, the first derivative, as you go to do that, the starting question, do I need to use product rule in this case?
Yeah.
Yes. Because in this problem, I have a function times another function. And anytime you have a function times a function, yes, you're going to have to use product rule. So when I go to use product rule to find the first derivative, that means I do the derivative of e to the x, which is just e to the x, times the cosine of x, left alone, untouched, plus, now the e to the x stays untouched, and I find the derivative of cosine, which is negative sine of x. Now, at this point, I could go ahead and operate on this to find the second derivative, but I never really like seeing plus and negative. I've just been trained over the years too long, I think, where it just bugs me. And so I want to go and change that into e to the x, cosine of x, minus e to the x, sine of x. Plus now when I go and find the second derivative, I just know there's going to be a minus in between them instead of a plus in between them. That's basically the only difference. And that is the next step, because this is a good answer for our first derivative right here. But notice you're also asked to find the second derivative. So please move on and find that second derivative now. Now when we go to find the second derivative in this case, people end up looking at it saying, wait, do I actually have to use product rule twice? Basically, the short answer is yes. There's a longer answer that I'll kind of touch on after we talk about this. But yeah, basically, yes, you're going to have to use product rule twice. You have to use it once to figure out what's the derivative of e to the x cosine of x. Although, actually, this is a lot easier than you might at first think, because the derivative of e to the x cosine of x, notice, that's what we found the derivative of already. We did that already. So I already know what that derivative is. It's e to the x cosine of x minus e to the x sine x. I did that work already. All right, so now, since I did that derivative, now the minus just carries down. So I got a minus. Now I do the derivative of e to the x sine x. And there, yeah, I actually got to do the whole product rule and actually think through it. So derivative of e to the x is e to the x, and that's times sine of x. And then plus, now we do e to the x times the derivative of sine of x, which is cosine of x. Now, I want to see how well you're catching a little detail. I just purposefully, and yes, it was purposeful, made a mistake. Can you see where that mistake is? Yeah, the problem is that this plus is not going to stay a plus here. There's two different ways people deal with it. Some people will just say, oh, well, I know that's got to be a minus. Personally, I don't, though. Personally, I always say it's going to be minus the derivative of that second function. I tend to do it with parentheses. But either way will work. But make sure you include that you take that into account, or you're going to have some problems as we go forward. All right. Let's see here. Can I simplify that second derivative?
No.
Let's see here. I'm seeing some stuff that looks a lot alike. I'm seeing some e to the x cosine of x's, and I'm seeing some e to the x sine of x's. So yeah, there must be something I can combine here. So f double prime of x equals, let's start with the cosine of x here. So e to the x cosine of x, I got that there, and I got e to the x cosine of x here. When I combine those, what's that going to give me? 0. Because remember, I'm subtracting that cosine of x. So that's gone. Okay, what about e to the x and sine of x? Is that gone as well?
No. Not completely.
No, afraid not. Because it's negative e to the x sine of x minus e to the x sine of x. That's like a negative 2 e to the x sine of x.
No. Sorry, shut up.
All right, and so then that now is a final, complete answer. All right, now I'm going to go back in time just a little bit. You may recall that, but right before we started taking the second derivative, we were talking about, do we have to use product rule twice? And I said the answer is basically yes, but not entirely. There was another method you could use. If instead of taking the derivative of that, I could actually have changed that form of my derivative, my f prime of x, and I could have, yes, as a couple of you saw, I could have factored out that e to the x, and that would have given me cosine of x minus sine of x inside the parentheses. We still have to use product rule in this case, but we only have to use product rule once if we do it this way. So which one is easier? Well, what kind of mood are you in that day? It's a personal preference thing. Some of you are going to say this is much easier. It's much easier just to use product rule and product rule. Some of you are going to say it's much easier to just use product rule the once and deal with the derivatives of each of these two separately as they come up separately when I do that particular derivative. It's a personal preference thing. But if nothing else, I want you to be aware that you have that option. All right, so in this problem, we're asked for what values of x does the graph of f have a horizontal tangent, and we're given a function. You notice how we just made this problem a little bit easier, though, based on the way that we've been doing some of our problems today? Notice this is the exact same function that we just dealt with in the last problem. That's going to make our lives easier. If I want to find where it has a horizontal tangent, what's the very first thing I need to do with my equation?
Derivative.
Find the derivative, absolutely. I see that word tangent, and I'm automatically thinking derivative. Well, this is where life is easier from the work we just did. I already know what the derivative is. And notice I'm just wanting the derivative, not the second derivative. I already know that f of x is e to the x cosine of x minus e to the x sine of x. All right, now the next thing is that we're specifically looking here where the tangent is horizontal. Now, how do I try to figure out where the tangent is horizontal?
Plug in 0 for x.
Yep, we plug in 0, but let's be very specific because this is where we can get into trouble. We do not plug 0 in for x,
For f prime of x.
we plug it in for f prime of x, yes. Because remember, f prime represents the slope. So I'm now going to go 0 equals e to the x cosine of x minus e to the x sine of x.
But then wouldn't it just be
All right, now, as we go and look to solve this, there's actually a couple different strategies that people might come up with. Some people will actually think first about moving this e to the x sine x to the other side, and then we could divide both sides by e to the x. That's a possibility. It's not the most common possibility, though. The most common possibility is actually factoring out e to the x. That's what most people come up with as an idea. So we get e to the x times cosine of x minus sine of x. Now, remember when we solved quadratics, we'd end up with a parenthesis times a parenthesis, and we could solve a quadratic that way nice and easy because if either of those parentheses equaled 0, then we know we had a solution where the whole thing equaled 0. And so basically I'm in the same situation here where I'm saying what makes e to the x equal 0 or what makes cosine of x minus sine of x equal 0. Now for the e to the x part, think about what the graph of e to the x looks like. This is your graph of e to the x. When does it reach 0? It doesn't. It never actually hits 0. We have an asymptote at 0 on this one. And so, because there's an asymptote at 0, it never actually hits 0. And so the e to the x part of my equation isn't going to give us any solution. Now because of that, I know that all I'm left trying to figure out is what makes the cosine of x minus sine of x equal 0. And depending on which way your brain works, you could just be thinking about it as, okay, cosine minus sine equals 0, or the way I prefer to think about it, I actually add sine to both sides, and I see it as sine of x equals cosine of x. So I know that this whole equation will equal 0 when sine equals cosine. So then the question is, when does sine equal cosine? All right. Now as you see that and you're trying to figure out when does sine equal cosine, you're all of a sudden brought back to remembering your unit circle work that you did a year or two ago. And hopefully you have some memory of seeing this, right? Now of course this is that whole big picture. There's tons of complexity here. And you haven't dealt with it in a while, so it's probably looking a little bit overwhelming. But of course this is all stuff you've seen before. It's just been a long time. But remember what we're looking for here. We are looking to see when does sine equal cosine. So just start looking around the horn. Where does sine equal cosine? I see one right here where sine equals cosine. They both equal root 2 over 2. Notice where that happens? Pi over 4. So x equals pi over 4. And if that were the end of the story, this probably wouldn't be too bad. But it's not the end of the story here, because that's not the only solution I see in this picture. Yeah, notice there's another point where they both are the same, where they both are negative root 2 over 2. By the way, notice this one does not work because one of them's negative, the other one's positive. Same problem happens down here. And so another possible solution is 5 pi over 4. Okay, what's another solution?
9 pi over 4.
And another solution, and another solution. Because notice, basically I can go from my original pi over 4, I can go around the circle, halfway around. And from that point, I could go halfway around again. And from that point, I could go halfway around. Yes, we could even go the other way around. So, notice I'm going halfway around the circle. What is half of a circle in radians? It is pi. Half of a circle is pi. So, I do pi over 4 plus pi times k, where k is any integer value. And that is our actual solution, because I can go around pi, that is around half the circle, as many times as I want in either direction. I'm still going to end up with sine and cosine equaling the same thing.